All right. So last time we were talking about kind of the history of programming languages, right? Talked about memory. Oh, we learned about the bits, bytes conversion, all that jazz. Okay, so let's start by talking about data representation. So I want to put us in a mode where we start thinking about using something to represent something else. You know, I kind of think back to um, when I was a kid playing Monopoly, and my brother always wanted to be the thimble, and we lost the thimble. So he made his own thimble out of aluminum foil, and it didn't look like the original thimble, but that was his piece. So he used this like made up thing to represent his thing in the game. And we all knew that it meant that, right? Even though it wasn't the original thimble. So throughout the way we do things in our daily lives, we're doing that kind of stuff all the time, and we don't even necessarily think about it. So let me give so if I give you the number like 146, what does that mean to you? What's a number to begin with? If you had to give a definition of a number. I heard somebody over here. Go ahead, somebody. Represents a value. Okay, what kind of value? What does 146 mean to you? What kind of information is it conveying? Go ahead.
Quantity.
Okay. Quantity and amount, magnitude, something like that. Similar if I say, what if I said 146 miles per hour? That like means something, right? You're thinking immediately, okay, it's a car, it's a motorcycle, something traveling at some speed. Now, why did I say miles instead of kilometers? We're Americans. Okay. But if I had said 146 kilometers per hour, at the very least, we all know that, okay, that's also a measurement of speed, right? Okay. So we have all these different things that we use to kind of give meaning to something, even though those somethings themselves don't have that much meaning unless we define what they're supposed to do. All right. So why am I choosing? So when I say 146 like this, let's break this down. So 146 just in and of itself. This is 100. Well, this is 1 times 100. So I have a 100. I have a 1 in the 100s place. This is the 1s place, the 10s place, and the 100s place. So I have a 1 times 100 plus a 4 times 10. So I have 4 groupings of 10 plus 6 groupings of 1, right? And you do all that math and add them all together, you get a 146. Felt like a waste of time, but that's effectively what that 146 meant. It's a single way of describing a single grouping of 100, 4 groupings of 10, and 6 groupings of 1s. It's a way of representing that, right? Okay. And as he pointed out, we think about that, and that might be a quantity, a number of something. It could be a value that then becomes associated with a speed if we throw more modifiers on it, like miles or kilometers, that kind of stuff. Okay. Well, why did I choose? Well, this 146. That is, since I've kind of described it here, this is the 1s place, the 10s place, the 100s place. This is in base 10 number system, which we call decimal, right? All right. Why do we use decimal numbers? Why do we use base 10 numbers? Yeah, 10 fingers, 10 toes, right? When you're a kid and you start thinking about your count, like, okay, 1, 2, 3, we use our hands to count, right? So it's compatible with us. And all the sci-fi books I read, the aliens always have 8 fingers, 4 in each hand. So they always use base 8. That makes it extra, whatever. We're going to learn about all these different bases in here. But the reason why human beings have landed on decimal is because we have 10 fingers and it's easy for us to count that way. That's why we've chosen to use base 10. Humans have 10 fingers. So we like this base. Computers use base 2, zeros and ones. Base 10 is 0 through 9. That's the language of our decimal number system, right? The digits 0 through 9. We make up all decimal numbers using those 10 digits. We make up the bits that make up the binary number system are zeros and ones. That's the language of the binary number system. Why do computers use base 2? Yeah, on and off state, digital logic. Okay, so on and off state for blah, 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 for digital logic. All right, it's compatible with our computers. So we picked a numeric representation language of binary for computers because it's compatible with them. We pick a numeric base for our counting because it's compatible with us. Now there's more bases than just those, right? It's more bases than base 2 and base 10. We also have base 3, base 4, base 5, base 6, any sort of base that we want in between base 1 and base 37. After that, we start running out of letters of the alphabet, and that'll make sense if you've never done this kind of representation stuff before. And what I mean by that is base 10 supports the language 0 through 9. Well, what about base 11? Base 11 would be 0 through 10, but 10 is 2 digits long. So we need to replace that 10 with another representation. So we use an A from our alphabet. So an 11 is represented by an A. A 12 is represented by a B, so on and so forth. Okay? So what we want to know how to do converting bases. Well, let's call it converting between bases. So going from decimal to any other base, going from any base back to decimal. Decimal being the highlight there because that's going to be our comfort zone. Okay? So that means we're going to have 2 patterns that we need to learn. You don't need to learn, oh, how do I convert binary to decimal? And then how do I convert octal to decimal? Then how do I convert hexadecimal to decimal? It's one pattern that you use to convert any base to base 10. Okay? And that same pattern will work for converting base 10 to base 10. Very boring, but it also works. So we have similarly, we'll have a identical, well, a different but consistent pattern from going from decimal back to any other base. So for example, I've used the number 146 here, right? So if we want to say 146 base 10 to base 2, I want to convert this into the binary number system. When I go from decimal to any other base, so let's just create a separate slide for this. I'm going to call it any other base n. Divide the decimal number by n over and over, recording the remainder and reducing n until it is 0. Read the answer from bottom up. All right, we're going to see this as an example here in a second. So what we're going to do in order to convert 146 to base 2, we're going to start with our 146. Hold on, I want to divide the decimal number by n over and over, reducing the decimal number, not n, until it is 0. So we start off with 146, which is our base 10. We're converting it to base 2. So we are going to divide it by 2 over and over and over again. So 146 divided by 2 is 73. So I'm going to record the 73 right here. Then I'm going to say 73 times 2 is equal to a 146. So we have a remainder of 0. Now we're going to say 73 divided by 2. 73 divided by 2, this is 36. 36 times 2 is 72. So to get to 73, we have a remainder of 1. $36 divided by 2 is 18. 18 times 2 is 36. So we have a remainder of 0 to get us to 36. 18 divided by 2 is 9. 9 times 2 is 18. Remainder 0. 9 divided by 2 is 4. 4 times 2 is 8. It takes 1 more to get to 9. So we have a remainder of 1. 4 divided by 2 is 2. 2 times 2 is 4. Remainder 0. 2 divided by 2 is 1. 1 times 2 is 2. Remainder 0. 1 divided by 2. How many times does 2 go into the number 1? 0 times. 0 times 2 is 0, with a remainder of 1. We know we're done when we've whittled our number over here down to a 0. So our final answer, we read from the bottom up. 1, 0, 0, 1, 0, 0, 1, 0. That is the binary equivalent of 146. Go ahead. The whole thing? No. We're going to do it several times. Why don't we do it with a different number? Just so we have a second example. Okay. So other questions about this one other than do the entire thing again? And we're going to do it several times with different bases. All right, so let's do another one. Pick your favorite 2 or 3 digit decimal number. 72. Okay. We actually already kind of have that one built in right here from what was it here? Oh, close. That's fine. 72 decimal to binary. All right. So we start off by writing down our starting number. Our goal is to whittle this number down to a 0. Okay. Now I keep saying things like we have a whole number, then we have a remainder. Remember 3rd grade math when you did long division? You all love that, right? Okay. Well, now it's come back to haunt you because that's what we're doing with. This is integer division. When we divide 72 by 2, I get a 36 remainder 0. Okay. Because 2 goes into 72 36 times exactly. So that's why I wrote down a 36. And then I said, to check it, I said 36 times this 2 right here is a 72, which is equal to what we were going for. So I have no remainder. It's a remainder of 0. You can also see it on the calculator when you do the math. and it comes out to a whole number with no decimal point after it, it's going to be a remainder of 0. All right, so we'll go ahead and record our remainder of 0 right here. So now, is 36 equal to 0? Not yet. So we'll divide that by 2. 36 divided by 2 is an 18. And it was 18 flat, no decimal places, so it's going to have a remainder of 0. We can test that by saying 18 times 2 is 36, which is the same as here, so we have nothing left to get us to there, so that's a remainder of 0. 18 divided by 2 is 9. 9 times 2 is 18, so that's another remainder 0. Now 9 divided by 2 is a 4.5, but we're doing integer division here. So 9 divided by 2 is a 4 with a remainder of 1. Okay? So 9 divided by 2 is the whole number 4, not 4.5. That would be floating point math. 9 divided by 2 is 4. 4 times 2 is 8. That gives us a remainder of 1. Go ahead.
So if it's anything other than just say
Try not to give a rule to it right now, but since we're going to binary here, the remainders are always going to be 0 or 1. Okay, because the whenever you're doing something to a base n, the remainders will be 0 to n minus 1.
Oh wait, so you're just dividing by 2, divide 9 by 2, 4.5.
Well, right, because since we're doing integer division says we don't know how to store decimal places. So yes, you're right. 9 divided by 2 is 4.5 by real math. Okay, but if we're doing integer division, if you go back and you remember, remember the picture, it looked kind of like, can they even reproduce it? We'll use we'll reminisce back to 3rd grade. Remember we had that guy, right? And we had you would have the 9 under here, and you'd have the 2 under there. And then you would say, how many times does 2 go into 9? 2 goes into 9 4 times. And you'd say 4 times 2 is 8. Oh, we have to have another line here, right? You subtract those, you get a 1. That guy. So then up here, you would write 4 remainder 1. That guy. Remember that? You gotta think way back, right? Yeah. Okay. That's what we're doing here. We're doing 3rd grade math. We're doing integer division, recording the quotient and recording the remainder, the integer quotient and the remainder. All right. So that's why 18 divided by 2 was 9, remainder 0. Because 2 goes into 18 9 total times with nothing left over. 9 times 2 is 18, so we don't need any extra stuff to get to 18. 2 goes into 9 4 times. 4 times 2 is 8. We do need an extra 1 to get us to the 9. 4 divided by 2 is 2. 2 times 2 is 4, so this is a remainder of 0. 2 divided by 2 is 1. 1 times 2 is 2. Takes nothing else to get us to 2, so that's also a remainder of 0. 1 divided by 2, and this will always be your finishing ninja move, is something that's smaller than what you're dividing it by. So 1 divided by 2, 2 goes into 1 0 times. Oh yeah. 2 goes into 1 0 times. 0 times 2 is 0, with 1 more to get us to that. We know we're done when we see a 0 right here. And then we read our answer from the bottom up. 1 0 0 1 0 0 0. Bottom up when you do it this way. It's the common mistake somebody will make, because they'll do all this stuff right, and then you'll give you an answer of 0 0 0 1 0 0 1. And that answer is well, it's not the right answer because that's backwards. This is a binary number. It's just a number 1 0 0 1. All right, so that's 2 times going from base 10 to base 2. Well, now what we're going to do is we're going to apply the exact same math, the exact same pattern, and just go to a different base. So let's take that same 72. Actually, just so we make it a little longer, let's do our 146. 146 decimal. So we're going to call it octal. This is base 8. Okay. So we're going to start off with our 146. But this time we're going to be dividing it by 8. Instead of 2, we're dividing it by 8 because we're going to base 8. All right. 146 divided by 8 is 18. 18 times 8 is 144. So we have a remainder of 2. Takes 2 more to get us to 146. $18 divided by 8, 2. 2 times 8 is 16, with a remainder of 2. 2 divided by 8, you'll always have that last finishing move where you're trying to divide your number by something larger than it. So 8 goes into 2, 0 times. 0 times 8 is 0, with a remainder of 2. It's a very convenient answer. I always run into those because now, if you haven't caught on yet, it could be confusing whether you read it from the top down to the bottom up. I promise you, the 2 I just wrote there is this 2 right here. Read it from the bottom up. 2 2 2 is the answer there. Okay, so 146 decimal is equal to 222 in octal. Now, it wouldn't be accurate for us to say 222. That's how we read decimal numbers, right? As we go back to how we represented, we say, well, we have 2 100s, and then we have 2 10s, and we have 2 1s. So we call that 222. But in octal, that's we don't speak. We don't have a verbal version of reading octal numbers. So we would just say that's 222 in octal. All right. But you do need to know, somebody needs to tell you that that number is octal, because this is a legal decimal number, is it not? So unless I told you we were representing this value using the octal number system, you have no way of knowing which base it is. You just know it's at least base 3. And you know it's at least base 3 because we're using 2s here. The biggest value you see in there is a 2. So the smallest base this number possibly could be is base 3, because base 3 supports the remainders of 0, 1, and 2. Base 5 represents the remainders of 0, 1, 2, 3, and 4. That guy. All right. So that's converting a decimal number to octal. See, it's the identical pattern, right? The only thing I changed is what I was dividing by. All right, so let's go Let's do 286 decimal to go base 4. All right, so take about 3 or 4 minutes and go and try to do this yourself. I'm not collecting it or anything, so just practice it and do your best, and then we'll go through it together. And I want to emphasize here, this is not just a parlor trick. This is critical to your computer science education, understanding this stuff. I have a feeling that Diet Mountain Dew is significantly older than I thought it was. Yeah, it's not so old that I won't drink it, but it's older than I thought. You can use your calculators on your phone or whatever. I'll always let you do that on tests. All right, so let's take a look at this. So same pattern as we've been doing, break down the 286. We're going to divide this by 4. 286 divided by 4 is a 71. 71 times 4 gets me 284, so I have a remainder of 2. 71 divided by 4 is a 17. 17 times 4 is a 68, so I have a remainder of 3. 17 divided by 4 is a 4. 4 times 4 is 16. Remainder 1. 4 divided by 4 is 1. 1 times 4 is 4, so that's remainder 0. 1 divided by 4 is 0. 0 times 4 is 0. Remainder 1. So the answer is 10132 in base 4. Go ahead.
Why don't you go down up this
Who? Why'd I read?
one?
Yeah, 10132. I read it from bottom up.
Yeah. You always go.
Yeah, always go bottom to top. Yeah, the only confusing one was this one where it was the same number all over, but
Okay.
yeah, this one was 1001000. It's always reading from bottom to the top. All right. So now let's go 2989 decimal to hex. This is base 16. Hexadecimal. All right. So go ahead and take a couple minutes and do this one. And you're going to come up with a okay answer, but not quite the right answer yet. So just go ahead and do it the way you've done it up to this point. All right. So the same thing, 2989. We're going to divide this by 16. And that's going to give us 186. 186 times 16 gets us 2976. So that's a remainder of 13, right? 186 divided by 16 is 11. 11 times 16 gets me a 176. That's a remainder of 10. So 11 divided by 16 is 0. 0 times 16 is 0 with a remainder of 11. Okay. So up to what we've done up to this point is we would write this out as 111013. And that's not going to cut it. We know, because we just did this, this is actually 3 different chunks. This is an 11, a 10, and a 13. But since those numbers are 2 digits wide, we need to have something else to be a replacement, a representation for those numbers. So 0 through 9 represent themselves. Those are single digit. But once we get to a 10, we start using the alphabet. So a 10 is an A, an 11 is a B, 12 is a C. So this is actually that's a B. That's an A. That's a D. So that is the hexadecimal value BAD. Go ahead.
They always
I would say the correct way of doing it is capitalize. It doesn't necessarily matter. So I guess to answer your question, I would say, no, it's not always capitalized, but it should be. Yeah, you'll see it either way, but a lowercase a doesn't mean something different. Now, you can start getting interesting though with it. And some of you have maybe played some games that try to represent gigantic numbers using something with extra letters and things like that. Keep in mind here that we've just decided to represent the number 10 as an A. Nothing keeps us from, coming up with a little rule with a friend that we actually are going to use the Klingon alphabet or something like that, or use other, symbols, emojis and stuff like that to represent different numbers. This just happens to be the common way of doing this. Okay. But we're just using the letter A to mean 10. Go ahead.
So in this case, like the lowest number is a second time.
10 is always an A, regardless of what base we're looking at. Or if I was doing this in base 26, a 10 is still an A. An 11 is still a B. And a 36 is a Z. Go ahead.
So for IPv6 addresses, then we use hexadecimal.
Well, so they do use hexadecimal. So IPv4, he's talking about IP addresses. So when you have IP addresses that go from 0 to 255, for the normal ones, that's IPv4, they're using decimal for that. When you go to one more number, then they're using hex to represent it. Otherwise, it'll be longer. So at the very least, we don't see a great example here, but 2989 here, that is a longer number than BAD. So we can think of going from base 10 to base 16, almost always will shrink the way to call that same number. Bad and 2989 mean the identical thing. We're just talking about that value, that magnitude in two different languages. We're talking about it in the hexadecimal language and we're talking about it in the decimal language. Two different ways of saying the same thing. Really no different than like English versus Spanish, right? We just have different ways of saying the same, having the same meaning. All right. So let me drive that point home a little. So before we go on the other way, common bases in computers. So we have binary, we have octal, we have decimal, and we have hexadecimal. Those are our common bases. So binary is base 2, octal is base 8, decimal is base 10, hexadecimal is base 16. Okay. Now we already answered why binary. Computers like this. Digital logic. Decimal is humans like this. 10 fingers. All right. So remember, all this stuff we're talking about here is how do we tell a computer what to do? So at the very least, we have to have the included languages of the language the computer likes and the language the person likes. Okay, so now what about this other crap? All right, so hexadecimal, I just gave you an example of, allows us to represent large values in smaller footprints. All right, and now let me tell you a little bit more about that, give you a real example of it. So All right. So I just wrote a little computer program here. Don't worry about what the logic said, but effectively I generated a memory address. So I created a variable that lives somewhere in memory, and I printed out what the memory address of that thing was. Now, what can you tell me about your computer's memory? I know last time we talked about, RAM and computers, right? 8 gigabytes, 16 gigabytes. Somebody here had 256 gigabytes, I think. But what does that mean? Let's say you have 16 gigabytes of memory. How does memory actually work in a computer? What's an address? If I say, you order a pizza and you give them your address, what information are you giving them? Yeah, a way of finding you, right? And our addresses in real life are complex. Now, so I'm trying to turn something around on you. For most of us, when you look at something like that, that looks scary. Big, complicated number. Oh, that must mean something smart. Okay, well, let's demystify that. This is an easy address. Human addresses are complicated. So when you give an address to your house for a pizza place, right? We give like 123 Oak Street. We give them the town. We give them the state. We give them the zip code. We give them the country. I mean, I know you don't need to tell Domino's what country they're going to, but you get the point. Your actual address is a pretty complex piece of information. It's what's the house number, on what street, in what city, in what state, in what country. That makes sense? That's a complex address. When you think about your computers, I want you to think about whether you have 8 gigabytes, 16 gigabytes, 256 gigabytes of memory, that the addresses, all the houses are on one big long street. You don't need to tell them a different street, a different city, a different state, a different country. It's just, what house number are you on the big long street? All right, that makes some sense. Now, having said that, if you have something like 16 gigabytes of memory, which by today's standards isn't that much memory, it's enough memory, but it's not that much memory. So if we have something like 16 gigabytes of memory, and we say, let's say the average memory address is, let's go with 8 bytes. Actually gonna so this memory address is 6 bytes because Linux, it reserves some memory. There's actually 2 different streets in our modern operating systems. One that's owned by the operating system only, and then the rest that's allowable for user information. For us, don't worry about it. Just one big long street. And let's just assume that the address is 6 bytes big. So if I have 16 gigabytes of information, so that's 16 times 1024 gets us to kilobytes, times 1024 gets us to bytes, divided by 6. So that's 2.8 million chunks of space on that street. So we can think of it as 2.8 million houses that live on this one big street. That's a pretty big number, right? For those individual houses. Now that's just us saying that we're going to represent them in six byte chunks. The reality is there's that many individual bytes, 16,777,216 individual little byte buckets that live in our computer's memory. So what we do is we represent the house number in hexadecimal. So getting back to your question, are they always in uppercase? Notice they're giving them in lowercase here. So this is the hexadecimal value 7FF7B3FF79B0. We can convert that to decimal. They'll give us an even larger value. And then we can use that value to, as a human being, walk that big long street to get us to that house number. Okay. But when we see scary stuff like this, usually we know it's a memory address if it has like a 0x before it. That's a hexadecimal representation. This is just a number. And the reason they chose hexadecimal is because the decimal version of that number would be even longer. This is scary enough. Really, we should make the argument, well, why don't they just make it, base 30, I'm going to go with base 31 for the moment for this argument, because that would be even smaller, right? So let's finish figuring this out. So remember this weird representation here in a few minutes. There's a reason why octal and hexadecimal are important players here. All right, so let's just go back to here. There we go. All right, so for right now, we're just going to leave it at hexadecimal allows us to represent large values in smaller footprints. Okay, it's also very compatible with something else, but we'll see that in a little bit. All right, now octal. Octal's kind of our weird one. We use octal, among other things, to represent things that can be written in 3 bits. There are 7, well, so the legal values for octal are 0 through 7. And to kind of give you an idea out here, we'll see another one in a bit. So these are the read, write, and execute permissions on an individual file. So we would use octal to represent, so 0 through 7 here tells us whether this thing is read, write, read, execute, read only, write only, or read, write, and execute. I probably missed a couple of combinations there, but there's 8 different states that can occur with those, and we use we use base 8 for that. We use it for some other things too, but we don't have the other side of the coin yet to give you that example. So for right now, let's just assume octal's a handy representation. All right, so these are common things for computers. We'll just throw some question marks on there for right now. Am I just not going to be able to save this document? Is that just today's deal? Perfect. All right, so we've learned one pattern now, right? So we can go from decimal to any other base up to base 37, right? Yeah, because 0 to 36. So 0 to 9, A through Z would be our legal representations for base 37. So I should be able to tell you right now to take any number we can take 2989 and say decimal to base 30. And you should be able to do it. So take 2 minutes, convert this. Remember that 10 is always A, 11 is always B, so on and so forth. And your possible remainders are 0 to 29. All right. So exact same pattern, right? 2989, but we're going to divide it by 30. 2989 by 30, that's 99. 99 times, oh, I'm going to do it 2989. Remainder 19, right? Okay. I cheated a little bit there if you saw. In most programming languages, the modulus operator, the operator to get you the remainder of an integer division, is the percent symbol. I just happened to try it in the Mac and it understood it. Other ones, it's other languages, it might say like mod. Yeah, it understands that too. So modulus is the remainder part of integer division. So 99 divided by 30, that's going to be 3. It's going to get me to 90 with a remainder of 9. 3 divided by 30 is a 0, remainder 3. So the answer here is 3, 9, and what's the 19th letter of the alphabet? J. That guy, 39J. All right, makes sense? Got a pretty good feel for that side of the equation. Decimal to any base whatsoever, as long as it's less than 30, so less than or equal to 37, you now know how to do. You don't have to memorize a different conversion pattern for each one. So now let's go to the other side. And then we'll close the loop. I'm going to give you a better reason why octal makes sense than the current thing. But you need to know the other side. And the punchline is going from octal directly to binary is very convenient. Going from hexadecimal directly to binary is very convenient. And vice versa. So the move between binary and base 8 and binary and base 16 is super convenient. You can skip the whole decimal part of it. That's why those are popular bases. All right, so if we want to go from any base to decimal, we write the initial number and then label the places for that number with the ones place at the far right. Then we multiply each place by the corresponding value and sum up all of the products. You're going to see this by example. All right, so let's take one of them that we've already done just to prove it. We'll take one of our easier ones. So let's take the this number right here. This should go back to 146 if we convert it back to decimal correctly, right? All right, so I'll start off by writing that number. And let's see, I'm going to have to spread it out some. So I wrote out my initial number. I'm going to go all the way to the right side here. I'm going to say this is the ones place. All right. So you always, regardless of what base is up here, on the far right, this is always the ones place. Okay. And then since we're going to, since we're going to decimal, what we do is we multiply, and we're currently in binary. We multiply by 2. So this is the 2's place, the 4's place, the 8's place, the 16's, the 32's, the 64's, the 128's. So I'll write it from left to right since it's easier to write it that way on here. So this is the 128's place. This is the 64's place. This is the 32's place. This is the 16's place. This is the 8's place, the 4's place, the 2's place, and the 1's place. So given that this is a base 2 number, and this is always the 1's place, we multiply by 2 as we go to the left to get us to the next place. So 1's place times 2 is the 2's place, times 2 is the 4's place, times 2 is the 8's place. We're multiplying by 2 because the number's currently in binary. Make sense? So once we have this written down, then we just do the math. 128 times 1 plus 64 times 0 plus 32 times 0 plus 16 times 1 plus 8 times 0 plus 4 times 0 plus 2 times 1 plus 1 times 0. And that's the number 146. You should get a 146 out of that. That's converting it back. Similarly, if I say BAD hex to decimal, I'll write out the BAD. Now the D is in the 1's place. The A is in the 16's place. The actually this is the 1's, the 2's. This is 256 place. So this is the 256 place. This is the 16's place. This is the 1's place. A different way of writing this, if you want to see it this way, is this is the 16 to the 2's place. This is the 16 to the 1's place. To the 1's place, and this is 16 to the 0's place. It'll come out to the same numbers. The previous one here, this was 2 to the 0's place, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. It'll come out to the same numbers. Okay. Now we need to remind ourselves, though, that a B is an 11, an A is a 10, and a D is a 13. So this is going to be 256 times 11 plus 16 times 10 plus 1 times 13. And this should give us 2989. It's the decimal equivalent. There's our 2989. All right, make some sense? All right, so let me give you one. Let's go. Let me try to trick you first. What's wrong with that question?
And number 8.
Yeah, can't have it. 8 is not a legal octet in the octal number system. Octal number system is 0 to 7. Decimal number system is 0 to 9. Hexadecimal is 0 to 9, A through F. So I'm just going to change this to a 7, or I can just say it's going to be base 9. But so we'll say 157 octal or 157 octal to decimal. And I don't care if you call them all digits, but officially a 0 or 1 is a bit. A 0, 1, 2, 3, 4, 5, 6, 7 for octal is an octet. Decimal, these are digits. Hexadecimal, they are hextets. Those are the official mathy names for individual characters in those languages. So convert 157 octal to decimal.
There's nothing about like, if you read it backwards going up, like you read it straightforward when you're writing it down.
Well, you're not really reading it straightforward because you're doing the result of a math problem, right?
Oh,
It's
right.
just a number that you're going to come out with. But yeah, there's not like a special thingy. All right, so let's look at this guy. 157. So this is, so it's octal. So this is the 1's place, the 8's place, the 64's place. So 1 times 8 is 8 times 8 is 64. So this is 64 times 1 plus 8 times 5 plus 1 times 7. $111. That guy. Oh, is that what you were asking? Because they happen to be the same 3 numbers. I have like an innate talent to pick random numbers that happen to convert to things that read the same. It happens every single semester. It's weird. Okay. So questions about that? All right. So now, so we got the 2 patterns, right? And that works for any basis. So in the last, well, probably only 50 minutes or so after we finished our early babble. So last hour, what have we done? We've learned how to convert any base to decimal and decimal to any base. That's not bad for a day's work, right? All right. So now that we got the hard stuff out of the way, let's go with the easy stuff. So what if I want you to do 157 octal to hex? What would you have to do? I don't want to waste a lot of time doing it right now. Yeah, so just do double time, right? Take it to decimal and then go decimal to hex. You can pull it off, right? Not the end of the world, just some tedious math, and hopefully you don't make mistakes, yada, yada, yada. I think I've mentioned to you before, every one of my exams you ever have, that's not just in this class, even as seniors, when you take my tests, I have conversion questions on them. You know, I know it might seem stupid, but I promise you, understanding these underlying languages and ways we represent stuff demystifies everything with technology. You know, in tech, we like to have really smart sounding things that mean easy stuff, a la that crazy looking memory address that's just a number of a house on a big long street. Okay, it's not difficult stuff, but we need to be unintimidated by this stuff. So since I have those in all my exams, a word of warning is always show your work. Okay. Even though some of these things, I know you can just tap out in the calculator or whatever, but if you do make that mistake, all my exams are 10 questions, 10 points each. All right. No multiple choice, no fill in the blank. They're just all short answer programming, whatever. Like I said, I have a midterm and a final, and I'll replace your midterm grade with whatever you get in the final if you do better. So you get a lot of opportunities. But let's say I ask you one of these conversion questions, which should be a layup, right? Free 10 points. Well, all of us in the moment of test pressure, right, can make a little math mistake. If you show me your work and you get the wrong answer, but it was just a little stupid mistake up top, maybe you get a 9 out of 10. If you just give me the wrong value, I got nothing. It's a 0, right? You know, show me you know how to do it. I realize that there's sometimes calculator fumbling during intense situations. So always show your work, even if you think you don't have to. Okay. All right. So let's do. Well, the reality is, if we're going to actually, this is even a kind of a fun one, because I'm going to show you the tricks. Or shortcuts. Octal to binary. Binary to octal. Hex to binary. Binary to hex. All of these can be done directly. You don't have to stop at decimal. All right, I'm going to show you why. Remind me, what are the legal octets in the octal numbering system? 0 through 7, right? So 0, 1, 2, 3, 4, 5, 6, 7. Octal, these are the Octets. Good band name. The Octets. From the 1950s, probably. That would be a good band name. The Octal Octets. Grunge band. All right. So 0, 1, 2, 3, 4, 5, 6, 7. 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. I promise you, if you go and do the conversion, these are the binary equivalents of these 8 octets. Notice that I was able to use in its entirety 3 bits to represent every single octet. And I've literally represented all of them. And I've used those 3 bits in their entirety. I have no extra bits left over. Make sense? So that means if I have, what was my number? It doesn't matter. If I have 130, whatever, 127 octal to binary, I can write it as, so this is a 1, a 2, a 7. So this is 0, 0, 1. This is 0, 1, 0. This is 1, 1, 1. That's the binary equivalent of 127. Because you can fully represent every octet using 3 bits. Exactly. Fully use the 3 bits. You can convert between octal and binary directly. Any octet you can write as its 3-bit binary equivalent. This is the 1's place, the 2's place, the 4's place. So this is the number 1. This is the 1's place, the 2's place, the 4's place. This is the number 2. 1's, 2's, 4's. Do all the math. That'll come out to a 7. Okay. Hexadecimal is the same thing, but you can do it in 4 bits. And if the streets get too long, we can switch to 5 bits, which is base 32. All right. Questions, comments, concerns, bribes. Okay, be prepared for a quiz at the beginning of class on Thursday, dealing with the stuff we talked about today. Not the shortcut ones, but going from decimal to any base and any base back to decimal. We'll practice the shortcut ones more, but those are easy ones, but you don't have practice yet. All right, I will see everybody on Thursday.